Hey y'all, Rusty Rob here. Welcome to another video. This time I'm going to go over one of the past Beta Hacker Cup problems, which is really interesting. So for those of you competing this year, I'm not competing, but I hope you're having fun and good luck for the round coming up this weekend. Maybe you can use this problem as practice. I was super happy to solve this problem because it's really hard and it meant I got a good ranking. And I managed to come up with a linear solution with a new algorithm that I haven't really seen before. So I think everyone else used segment trees and had n log n solutions, whereas this is a way to use a couple of different monotonically increasing queues or dequeues, and then kind of merging them together as we're traversing the tree. It's pretty interesting, and the implementation is pretty nice. So let's have a look at the problem first. So in this, I'll link to this problem, you can read through it. But essentially you start at a node and you're in a car and you've got a full tank of gas. Each edge we traverse, we use 1 unit of fuel. And every now and then there's gas stations that we can refill our tank. We pay the full amount and completely fill the tank. And we want to know what's the cheapest way to get to the finish node, if we can even get there. So maybe we skip past the expensive gas stations and we just go for the cheap ones. But then every now and then, if we run out of gas, then it's like, oh, maybe we go back to that expensive gas station and actually use that. So here's a drawing. And so here's a start node and a finish node over here. And we can have a queue of gas stations that's monotonically increasing. Each time we get to like a really good, like cheap gas station, then we can just pop off all the expensive gas stations from that queue. There's no points. Yeah, we can definitely be greedy there. And how do we know the cost to get to that gas station? Well, we can look at like the cheapest gas station in the queue so far, which is the leftmost one. And we know the cost to get to that one. And then we fill up, and then that allows us to reach the current station. And so now we know the cheapest way of filling up at the current station is just the cost of the current station plus the cheapest cost to get to that station. So as we're kind of traversing along here, that's what we're doing. We're basically just adding gas stations to our monotonically increasing queue and discarding gas stations that we know we can. But then when we get to a subtree, it gets interesting. We can kind of potentially go down, fill up, and then go back up towards the finish. It would be really nice if, say, one thing that's kind of interesting is this distance here. Like if we look at the distance from, like, let's say this node to the finish is the same distance as from this node, right? So wouldn't it be nice if we could just kind of move this gas station over to here, right? And so then if there's another gas station here and there's a gas station here, we'd just have the minimum cost here, right? And then we could use that to proceed forwards. However, we don't know if we can necessarily reach this gas station. So we kind of need to go along here and calculate the cost to get to this gas station, right? And once we have the cost of all these gas stations, then we can kind of move them across to here. So we kind of like have the minimum cost at each level of the subtree and then move that cost across to the original graph, and then we continue along. And now this seems really expensive. Like this could be a really tall subtree and this could be quite far. So that seems like it's going to be n squared. But actually, we can basically, if we have the height of this subtree, then we can basically take off all the relevant stations, and then we can do like a merge to merge those two monotonic queues together, just taking the best one each time. And the cost of that's just going to be 2 times h, right? And so each node in a subtree only contributes 2 to the actual cost. So the total cost will just be 2 times n, so it's linear, even though it feels like it should be n squared. So I thought that was a really cool algorithm, so I'd encourage you to give it a try. And I'll just